Alright, in this video we're going to start talking about moments of inertia. I want to kind of go first of all over what is moment of inertia. Then we're going to look at two methods of calculating moments of inertia. Somewhat similar to what we did with centroids. We're going to start off with an integration method, and then we're going to look at a composite area method for calculating moments of inertia. But before we get there, let's go ahead and look at what is moment of inertia and where does it come from. So this is just one example of a problem where moments of inertia would come into play. So for instance, let's consider we have this plate or some body submerged in a fluid and subjected to a fluid pressure P. So think about if you stuck your hand in water or if you dove into a swimming pool. The pressure at the bottom of the swimming pool here would be much larger than the pressure at the top. Actually, the pressure at the very surface level is 0, and as you go down into the pool, the pressure increases. It actually turns out that it increases linearly as a function of y. In this case, y, notice, is the depth of the body in the fluid. And here we have this linear constant gamma. That's just a fluid property of the material, or fluid material property, the specific weight of the fluid. So we have this pressure acting on the body, and let's say that we want to calculate the force from this pressure. Well, pressure is force divided by area. So in order to calculate the force, say on this strip of the area, we would have to take the pressure and multiply it by the area. So then we have the force acting on this differential area, pressure here times area. Then if we wanted to take the moment of this force about the x-axis, right, here's the x-axis, our moment arm in this case would be y for the force dF, and then the direction would be positive. So substituting in here, we have the moment is equal to y dF, that's the moment arm times the force. And then substituting for y, or sorry, not y, substituting for dF in terms of p dA, and then substituting for p, we end up with gamma y squared dA. So this is the moment of the force on this one little strip of the area. If we wanted to find the total moment on the body, we would need to integrate that moment over the entire area. So taking the integral over the entire area, we can pull out the specific weight. It doesn't vary with depth or with the area at all. And we would be left with gamma times integral of y squared dA. So this integral that looks like y squared dA, integrals of this form often arise in different mechanics problems. We have fluid mechanics like the one that we're looking at here, the example. We have mechanics and materials that will show up when you get a mechanics and materials course like deforms. Structural mechanics, mechanical design, it shows up all over the place, so we give it a name. In this case, for integral of y squared dA, that is what we call the moment of inertia, I sub x, of the area about the x-axis. So it's moment of inertia. Moment comes from the fact that we took a moment of the force. It's called area moment of inertia here because we are integrating with respect to the area, and then it's about the x-axis because that's the axis that we took the moment of the force about. So when you see the I, that means moment of inertia. Subscript x means x-axis. If we generalize this formula, here's what we end up with. We have some area, and looking at a small differential area, we can, for the moment of inertia about the x-axis, we take the moment and we get integral y squared dA. If we want the moment of inertia about the y-axis, then the moment arm becomes x, and we have integral of x squared dA. If instead we want the polar moment of inertia, that means we're taking it about some point O, and then in this case it's not x or y in the equation, it's r. We have integral of r squared dA. So looking at each of these moments of inertia, notice that we have here y, that's some distance, so we have a length squared times area, which is another length squared, giving us units for moment of inertia, length to the 4th power. Also notice that I and j are always positive, because here we have a squared term, and then area is always positive. So for moment of inertia about the x-axis, we have this equation. Moment of inertia about the y-axis, we have this equation. So what we want to do is, as I said, we're going to talk about how do we calculate moments of inertia using two methods. The first one we'll look at is the integral method, and we'll start that here in a second. Then we'll look at the composite area method later on. For the integral method, this is our general procedure for analysis. The first thing is to choose a representative element in order to integrate. So our representative element, we want to orient the element such that it touches the curve right at x comma y. So notice that both of these elements touch the curve at some x comma y. Then, for the direction that we orient the element, it's important to orient the element such that its length, right, its finite length, is parallel to the moment axis. If we don't do it this way, then we'll get the answer wrong every single time. So it's important, for instance, if we want to calculate I about x, that we orient the element parallel to the x-axis. So we're going to use a horizontal element for I about x and a vertical element for I about y. Then, whenever we define our element, we express dA in terms of coordinates x and y, and then solve for, this is actually meant to be I about x and I about y, using our equations. So let's walk through a couple of examples where we look at how to calculate moment of inertia using this integral method. So here's the first one that we'll look at. I know it says example A2, but I want to look at this one first. So, determine the moment of inertia of the shaded area about the x and y axes. So here's our area. It's bounded by three curves. At the left, we have y is equal to 0. At the top, x is equal to, at the left it's bounded by x is equal to 0. At the top, bounded by y is equal to 1. And then on the right side, bounded by the curve, y cubed is equal to x squared. So as it said, the first thing we need to do is set up the element. So we want to choose an element that touches the curve at some x, y, and in the case of I about x, we want to orient the element parallel to the x-axis. So this is the element we'll use for I about x. So what I like to do whenever I'm calculating the area, differential area, is I'll just draw a little sketch of the element. And on the sketch, I'll note a couple of key things. For instance, I'll note the coordinates at the left and the right side of the element. So right here and right here. So the coordinates should be representative of the entire area. So for instance, at the left coordinate, no matter where we are, no matter what y value we're at, we always have an x value of 0 on the left side here. For the right part, no matter what y value we're at, we always have an x value bounded by this curve, y cubed is equal to x squared. So the coordinate for the left-hand side would be 0, y, and the coordinate for the right-handed side would be xy. The other thing I want to give is, in this case, the height. Since this is a horizontal element, it has a differential height dy. Then all I need to do in order to specify the area now is to calculate the area of this rectangle. So the area of a rectangle is just width times height. In this case, the width of the rectangle is this minus this. So x minus 0, and then the height is dy. So now that we have our differential area, we can plug this area, dA, into the equation for I about x. And for I about x, we end up with something like integral y squared dA. That's the formula. Then plugging in dA, we have integral y squared. dA is x dy. Notice here we're integrating with respect to y, so we need everything in the integrand to be a function of y. This is a function of y, but we need to put x in terms of y. So in this equation, we would solve for x in terms of y by raising the entire equation to the power 1/2. So x would be equal to y to the 3/2 power. Then I can combine y squared times y to the 3/2 by adding the exponents. So 2 plus 3/2, 7/2. My integral is on y, so my limits should be based on the lower and upper bound of y for the area. So at the lower I have y of 0, at the upper y is 1. And then now I just integrate and solve as I would normally. So from the integral I get 2/9 y to the 9/2. Limits from 0 to 1. If I plug in 1, I get 1. If I plug in 0, 0. So this ends up just being 2/9 meters to the 4th power. So the units I just basically get from the dimensions here, it's meters. And then I know that moments of inertia should be length to the 4th power. So physically, it's really kind of hard to say, is this number right or wrong? Remember, with centroids, we were kind of able to justify our answer based on visually what we saw where the centroid of the body should be. But for moments of inertia, it's not really something that we can physically just say that looks right or that looks wrong. We just have to kind of trust the process. Alright, going back to our area, now we want to calculate moment of inertia about the y-axis. So for the y-axis, we want to choose an element that touches the curve at xy and that is parallel to the y-axis. So in this case, we use a vertical element like this. Again, whenever I'm setting this up, I want to kind of sketch a couple of the points and my representative element. So this time my element is vertical. I'm going to specify the coordinates at the top and at the bottom. My thickness here, since this is a vertical element, my width would just be dx. For a representative coordinate at the top, no matter what x value I have a y value of 1. For the bottom, no matter what x value I'm at, I have a y value that's bounded by this curve. So my coordinates would look like, at the bottom, x, y from the curve, and then at the top, x, comma 1. So to find the differential area, again, height times width. In this case, the height would be the top coordinate minus the bottom, so 1 minus y, and then my width is dx. So plugging this into my integral equation for I about y, I about y is equal to integral x squared dA. By definition, plug in dA, and I have x squared times 1 minus y dx. For the vertical element, I'm integrating with respect to x, so everything needs to be a function of x. Here I need to replace y with its function in terms of x. So if I solve this for y, I would get x to the 2/3 power. And then factoring out, I'll have x squared minus, add the exponent 2 and 2/3, that would give me x to the 8/3 power. This time my limits are on x. So I go back to my figure. At the left I have an x of 0, at the right I have an x of 1. And now again I can just solve it as I would any regular calculus integral. Integrate x squared and I have x cubed over 3. Integrate x to the 8/3. I'm going to get 3/11 times x to the 11 over 3. Plug in my limits of 0 and 1. And this ends up being 0.061 meters to the 4th. So as I said, there's not really a great way to check moments of inertia, the physical value. We just have to kind of trust the process and that we set it up correctly. So let's look at another example for moments of inertia just using the integration method. And now we'll look at this particular problem here. So it wants us to determine the moment of inertia of the shaded area about the x and y axes. So exact same problem statement as last time. This time, looking at our area, we want to kind of understand what the area is bounded by. So at the left-hand side, it's bounded by the curve x is equal to 1. At the right-hand side, x is equal to 4 for this lower part, and xy is equal to 4 for this upper part. So notice that at the right hand side it's bounded by two different curves. So we're going to have to end up and break this body into two different parts. Then for the lower, it's bounded by the curve y is equal to 0. In the upper, it's bounded by the curve xy is equal to 4. So we can just solve one integral there. Alright, let's do I about x first. I about x, I need to use a horizontal element, one that's parallel to the x-axis. So I set up for the lower part here, my element would look like this. For the upper part, it would look like this. So I'll have to break this up into two parts, right? In the lower section, I would be integrating something different than in the upper section. So you might be wondering, well, how do I find the total moment of inertia in that case? So here's what we're doing. I'm breaking Ix into two parts because we have two different curves at the right side. We can show, we're not going to show it yet, but we will here in a second, that if I want to find the moment of inertia of the body about x, I can take the moment of inertia of part 1 and add it to moment of inertia for part 2. So I don't have to do anything like I did with centroid, where we had that equation to find moment of inertia, or centroid of a composite area. For moment of inertia of a composite area, it turns out that I just need to add the moment of inertia of the parts. So we'll focus first of all finding ix1, that I defined as the top part, and ix2, that of the bottom part. So just like in the last problem, I like to set it up where I just kind of sketch my element. So since I have a horizontal element, it's going to have a height of dy, and then I specify the point values at the left and the right that are representative for the whole curve, or for the whole area. So for my element number 1, at the left-hand side, no matter what y value I'm at, I always have an x value of 1. For the right-hand side, given a certain y, my x value is bounded by this curve. So my coordinate at the left was 1, y, at the right, x, y. So calculating the area of this rectangle, dA, is going to be the width, which is the right coordinate minus the left, x minus 1, times the height, dy. In this case, since I know I'm going to be integrating with respect to y, because I have a dy in there, I might as well go ahead and put x in terms of y. So x in terms of y is going to be 4 over y. So I have 4 over y minus 1, and then dy. Then I plug it into my equation for moment of inertia about x is integral y squared dA. Plugging in what I have for dA. Factoring out, I have integral of y squared times 4 over y gives me 4y, and then minus y squared. My limits are based on y for the upper part. So for this upper section, the lower bound of y is 1, the upper bound of y is 4. So then I can take this integral, solve it, and for ix part 1, I get 9 meters to the 4th. I need to do the same type of thing for part 2. So for part 2, finding its representative coordinates and the height. So looking at the area, for part 2, that's the lower segment here. At the left-hand side, no matter what y value I have an x value of 1. At the right-hand side, whatever y value I'm at, I have an x value of 4. So my coordinate here would be 1, y. Here would be 4, y. Calculating dA. We have the width, which is going to be right coordinate minus left, so 4 minus 1, times the height, dy, gives me 3 dy. Substitute that into my formula for I about x, which is the integral of y squared dA. That becomes integral, the 3 I can bring out front, and then I have y squared dy. So, calculating this integral, first of all I need to specify the limits on y for the lower portion. For the lower portion, the lower y is 0, the upper y is 1. And I can integrate this to find 1 meter to the 4th power. putting all the information together and solving then for I about x of the body, I just take I about x for part 1, add it to I about x for part 2, and that gives me the total moment of inertia for the body. 10 meters to the 4th power. Lastly, I need to do I about y. So for I about y, we use a vertical element, one that's parallel to the y-axis, and touches the curve at the top and the bottom. So we can use an element like this. I can go ahead and sketch that element out, specifying the top point, the bottom point, and the thickness. So my top point here for the orange element, my x value gives me a y value based on the curve. At the bottom here, whatever x value I have, I'm always at a y value of 0. So top coordinate x comma y, bottom coordinate x comma 0. dA is then top coordinate minus the bottom coordinate, y minus 0, times the width, dx. Here I notice that I'm going to be integrating with respect to x, so I put y in terms of x already. So from the function, y is equal to 4 over x. Then I can substitute into my integral equation. I have integral of x squared dA. Substitute for dA. And I'm left with 4 outside, then integral of x dx. This time the limits are based on x. So at the left-hand side I have x of 1. At the right-hand side, x of 4. And to calculate this integral, what I should get is 30 meters to the 4th power. So that would be the basics of calculating moments of inertia with the integration method. All right, if you don't like using the single integral like I've shown here and defining dA based on the top and bottom coordinates for a vertical element and the right and left coordinates for a horizontal element, then of course you can use just a basic area element that's a small rectangle, or small square actually, something like this, and use a double integral for dA. That's perfectly fine as well. If you want to do it that way, go ahead. But either way, these are the ways that we calculate I about x and I about y. Now that we've kind of looked at a couple of examples, I think it seems that moments of inertia integration technique is actually easier than centroid integration technique. Right, because we just have one integral instead of 2. But as we'll see here in a second, remember for centroid, the composite area technique was very straightforward and simple. Whereas I think the composite area technique for moments of inertia actually is more difficult than the integration method. So before we get to the composite area method, I want to go into a little bit of a discussion on what's called the parallel axis theorem. So the parallel axis theorem is very useful for composite bodies. So first of all, what is the parallel axis theorem say? This is what it says. If the moment of inertia is known about an axis passing through the centroid of an area, then the parallel axis theorem can be used to find the moment of inertia of the area about any axis parallel to the centroidal axis. So that's kind of wordy, right? Really what it means is this. So let's say that for this body, I was given, or I had somehow already calculated, the moment of inertia of the body about some centroidal axis x hat. And then I wanted to calculate moment of inertia about a parallel axis, x. Well, the parallel axis theorem will allow me to do that very simply. So let's go ahead and derive the parallel axis theorem, and then we'll talk about how do we use it with composite areas. So notice here I have the centroid of this area, and then this is just some differential area, part of the area. For the centroidal axes, notice that I give a unique notation. I have here x hat and y hat. So I use the hat notation with the axes to specify that that is a centroidal axis and not a regular x or y axis. And then down here I just have some regular x or y axis, wherever they may be. So for the centroid, right, the area, it has coordinates in the x hat, y hat frame of some x0 and y0. Then the coordinates of the centroid in the xy frame of reference are, of course, x bar and y bar. So let's calculate the moment of inertia of the area about, say, the x-axis. So our normal equation, I about x, would be integral of y squared dA. So the y coordinate would be a combination of y bar plus y0 for the area. So then I plug that into my equation, I about x. Here's integral of y squared dA. Y bar plus y0, that's y. And then I square this. This is a polynomial, so I'll have 3 terms that come out of it. And I'll look at each of the terms individually. So for the first term, whenever I have the y0 squared times dA, that is the moment of inertia about the x hat axis. Right? It's like integral of y squared dA, but here it's y0, so that's the moment of inertia about this x hat axis. The second term, 2y bar times integral of y0 dA, actually turns out to always be 0. I'm not going to prove it, but it can be shown it always turns out as 0. The last term, whenever I have y bar squared dA, well, y bar squared, that's just a number, so we can pull it out of the integral. Integral of dA is just the area. So then this becomes y bar squared times a. So for this particular body, I about x would be equal to I about x hat plus y bar squared times a. Now we want to generalize this parallel axis theorem for any body and any set of coordinates. So in general, what we have are these two equations, which we call the parallel axis theorem. So we have I about x. That is some new x-axis that we're trying to move to. It's called the parallel axis. So to go to any parallel axis, we start from the body's centroidal axis and calculate the moment of inertia about the centroidal axis. Then to move it to the new axis x, we have this parallel axis theorem part. We have plus the area and then times some d squared, where d is the perpendicular distance between the old axis and the new axis. Likewise for y, we have I about the y centroidal axis plus area distance squared where the distance here is between the y-hat axis and y. So a couple of notation things. Remember that x-hat and y-hat, that's what I use for the area's centroidal axes, so they pass through the centroid. X and y are the arbitrary x and y axes as normal, and of course C is the centroid of the area. And then these terms we also have explicitly defined here. So what is the whole purpose of the parallel axis theorem, and why do we have it? Why is it particularly useful? Well, when we use it in combination with composite bodies, it turns out to be extremely useful. Just like with centroids, for areas such as a rectangle, triangle, circle, things like that that are common shapes, the moment of inertia is already calculated for us about the body's centroidal axis. So in essence, we're already given this term for different simple shapes. So to find the moment of inertia of that shape about a new axis, say the x-axis, we can just use parallel axis theorem to move it to the new x-axis. Which, along with moments of inertia for composite bodies, we've already kind of seen, that's how we find moment of inertia for a composite body. So, for instance, I about x is sum of I about x for all of the parts. I about y is sum of I about y for all of the parts. Whenever we have a composite body, this is kind of the general procedure that we're going to go through. And we'll walk through this very slowly, step by step, with several examples. First thing, divide the area into composite parts and find the centroid of each part. Second, use the parallel axis theorem when needed and move the moment of inertia from the local centroidal axis to the moment axis. Third, sum up I for each part, remembering that wholes have negative values. And then lastly, table D3 can be used for the calculation of I about x hat and I about y hat of the simple shapes. So for instance, if you look up a rectangle in table D3, this is somewhat like what you'll see in the back of the text. We're given the centroid location right in the middle. Here's the dimensions of the rectangle, and it gives us the value for I about x hat and I about y hat, right? Just as 1/12 bh cubed for x hat and hb cubed for y hat. For triangles, we have here the centroid location we know as b over 3 h over 3 in the x and y coordinate frame. Moment of inertia about the centroidal x-axis is given. Moment of inertia about the y centroidal axis is given here, based on the dimensions of the triangle B and H. Another one that we're going to use, a circle. We're given the centroid location right in the center, and then I about x hat, I about y hat happen to be the same for a circle. So what we want to do, we're going to look at several examples. The first one that we're going to do, I'm going to go through in a little bit slow way, just so that we can get all of the details and really understand what's going on here with moments of inertia for a composite area. Right, we're going to use a combination of these reference figures, our equation for moment of inertia for composite bodies, and our equation for parallel axis theorem. Alright, this is the first one that we're going to look at. It wants us to, as before, determine moment of inertia about the x and y axes. So setting this problem up starts off like we would set up a centroid problem. We just look at the area and divide it into the least possible number of simple shapes. So I specified here a rectangle, which are called part 1. a triangle, which I call part 2 over here, and another triangle, which I call part 3 at the top. Once I have my areas set up, I'm going to go into an in-depth analysis for each of the areas. And I don't have to do this every time I'm calculating moment of inertia for a composite area, but at least at first, when I'm new to these problems, I think it's a good idea to really look in depth at each of the parts. So we'll go part by part. First of all, we have part 1. So I like to just sketch out my parts, and I calculate 4 quantities. So here's part 1. I'm going to locate the centroid of part 1. Here I'll label that as C1. I'm also going to sketch my reference axes, x1 hat and y1 hat. So notice the notation here. x1 hat means that the x hat means it passes through a centroidal axis. The 1 subscript means it passes through the part 1's centroidal axis. So based on the body, what I want to do is compare it to my reference figure. For a rectangle, I need to know the dimension b and the dimension h. So for this particular part, part 1, I want to know what is its base and what is its height. So the base dimension is 3, the height is also 3. Once I have this, I like to calculate 4 quantities. I want to specify the centroid, the area, the moment of inertia about the centroidal x, and the moment of inertia about the centroidal y-axis. So there's a reason I do each one of these things, and it'll become clear later on when we put all the information together. So first of all, the centroid. Location of part 1 centroid, just remember we've already done this before. In the x direction is at 3 over 2, and in the y direction also at 3 over 2. So the body, or actually the part's centroid, is at 1.5, 1.5. Remember in our previous notation, we called the part's centroid x tilde, comma y tilde. For area of a rectangle, I have base times height, which in this case gives me 9 inches squared. For I about x hat, I go to my reference figure. I about x hat for a rectangle, 1/12 bh cubed. So I just literally copy that down, 1/12 bh cubed. Calculate it for my b and my h of the part, which is going to give me 6.75 inches to the 4th. For I about y hat, again I use my reference. I about y hat is 1/12 hb cubed, so I switch the h and the b. In general, this should give me a different number, but in this case, b and h are the same, so it gives me the same 6.75 inches to the 4th. Alright, once I specify these 4 quantities, I'm going to move on to the next part, and then I'll put the moment of inertia back together again at the end. My next part is part number 2, which is a triangle. I kind of sketch it out first. Again, I'll show where the centroid is. This is going to be centroid 2. I like to show the centroidal axes that I'm taking moment of inertia about. So here I have x2 hat and y2 hat. From my reference figure for a triangle, moment of inertia about x hat and y hat, I need to specify again b and h. So the base dimension of the triangle and the height. So here for part number 2, its base is 6, its height also happens to be 6. Then I go about specifying the same 4 quantities: centroid location, area, I about x hat, and I about y hat. So I'll locate the centroid of part 2. In the x direction, I have to get to the left edge, so 3 plus the right angle is right here, so then 1/3 of 6. So this gives me 5 in the x. And y, I'm already starting off with the x-axis at the base, so I just need to go up a distance of h over 3. Remember, I stay close to the right angle. So 2 for y. My area of a triangle, 1/2 base times height, which in this case will give me 18 inches squared. For I about x hat, I use my reference figure. I have 1 over 36 bh cubed. That gives me 36 inches to the 4th. For I about y hat, I have 1 over 36 hb cubed. So again, in general, I about x hat and y hat are different numbers, but in this case, since h and b happen to be the same thing, I about x hat and y hat are the same. Then I'll go through this same type of process for part number 3. So for part number 3, I'll just go ahead and pull it in since I already have it prepared. I sketch out my body, locating the centroid and giving same reference dimensions b and h, because I still have a triangle. Notice this time the centroid location, since the right angle is on this side, it should be closer to the right angle side, so it's going to be 2/3 of this base dimension 3. And then for y tilde, first of all I have to get up to the base, so 3 plus, then keep it close to the right angle, 1/3 of the height 3. For area, I have here 1/2 base times height. So I'll just use notation here, b times h. For I about x hat, I have 1 over 36. This should be b, this is h cubed. And for I about y hat, I have 1 over 36 h b cubed. So now for each of my parts, I have 4 terms defined. And what I'm going to do from these 4 terms is I'm going to put the moment of inertia about x and y axis together, right, using the composite area method. So first things first, I have my composite area equation. I about the x-axis should be I about the x-axis for part 1 plus I about x for part 2 plus I about x for part 3. Then, for each of the moments of inertia, for instance, I about x for part 1, notice what I have for part 1 is I have I about x hat 1, not I about x. So I need to take and move the moment of inertia from the x1 hat axis to the parallel x-axis. So I'm going to end up using a parallel axis theorem to do that. So it should look something like parallel axis theorem equation. To remind ourselves, we have I about the centroidal x-axis plus some area times a distance squared. So I'll just write this out first of all. I have for part 1 from its centroidal axis, then I add the area times some distance squared. So this whole thing right here is I about x for part 1. I'll have for the other two parts similar equations. I'll have I about x hat, and then from the parallel axis theorem I need to move it to the x-axis. So looking at this equation, I've already defined these three terms, I about the x hat axes for each of the parts. I've defined the areas for each of the parts. So the only thing left is to specify what are the values dx for each of the parts. So remember from the parallel axis theorem stuff that we talked about earlier, this dx is the perpendicular distance from the centroidal axis to the new parallel axis. In other words, it's the distance between this axis and this axis. Perpendicular distance. So, for instance, to go from this dx1 should be the distance in between x1 hat and x. Right? If we want to sketch it out, what I can do is I can grab the original figure. I'm just going to select this and I'm going to copy it downwards, down here. And I'm going to sketch in the centroid of part number 1. It was somewhere in here. And copy my centroidal x1 and y1 axes. So notice I want the distance between, for part 1, x1 hat and x. That distance I've already calculated. It's what we call y tilde. Right, the y location of the part's centroid. And for the other parts, it's going to be exactly the same. So I can get that dxi is just equal to yi tilde. So dx for part 1 is equal to y1 tilde, which I happen to already have specified right here. It's 1.5. For part 2, y tilde is 2. And for part 3, y tilde is 4. So kind of just rewriting this all out, I can get I about x. So it would look something like this. I take I about x hat for part 1, which was 6.75. Then I have plus area of part 1, 9, times dx1 squared. So y1 tilde, which is dx1, 1.5. And then I square that. For part 2, I have I about x hat, 36, plus area 2, 18, times its distance squared, which is y2 tilde, 2. And then for part number 3, I have I about x hat, which is 2.25, plus area of part number 3 was 4.5, and then y3 tilde we found as 4. Calculate this number, and I end up with the answer 209.25 inches to the 4th. So for moments of inertia composite area, we have to use the composite area equation, which basically just sums up moments of inertia for each of the parts, and that gives me the total moment of inertia for the body. And we also have to use parallel axis theorem based on we're given information I about some x hat axis, and then we move it to the new axis. In this case, we're moving it to x. So what it would look like for I about y. For I about y, we have, first of all, the composite area equation. We have the moment of inertia about y-axis for each of the parts. And then, for instance, for part number 1, we don't have moment of inertia about y. We have moment of inertia about y1 hat. So we have to move it with the parallel axis theorem by doing some plus a times a distance squared. And likewise for the other two parts, we'll take the moment of inertia about the centroidal axes and then move it to the y-axis. So like before, we've already defined most of these terms. We define I about the local centroidal axis for the part. We define the areas. So the only other thing that we need to get is what are the values dy for each of the parts. So the value for dy should be the perpendicular distance between the old axis, so the y hat axis, and the new axis, y. If we go back to this figure that I showed a second ago, what's the distance between y1 hat and y? That's what we call x tilde. The x location of the part's centroid. So for our dy, it's just going to be x tilde for the part. So substituting in all the expressions for x tilde here, I about the y's that we've already defined, and a, check and make sure that we get I about y equal to 533. So for our composite area method, we have to use a combination of the composite area equation, adding moments of inertia for the parts up to get the total moment of inertia. And then we have the parallel axis theorem to use moments of inertia about a centroidal axis that's given and then moving it to a new parallel axis. So that's kind of the basics of the composite area method. There's a couple other things that I want to point out along the way about some problems, how they're different than others. I want to look at one problem that has a hole, and I also want to look about what if we're asked to find moment of inertia about some other axis besides the x or y axis. So I want to take a look at this problem here. This one's asking us to determine moment of inertia about the x-axis, about the y-axis, so that's as we've been doing. But then it also asks us to determine moment of inertia about the centroidal x and centroidal y-axis. That means the centroidal x-axis of the body and the centroidal y-axis of the body, not of a particular part. So that's where it's going to be a little bit different than what we looked at in the last example. So I'll set this problem up and I'll run through some of the basic calculations at the first. But the main thing I want to talk about here is how to get I about centroidal x and I about centroidal y axis. Alright, first thing, I need to separate the body into parts. I want to try to choose as few as parts as possible. So one way to do this would be to specify a rectangle here, triangle here, and then a hole of a circle. But a shorter way to do it would be to use a rectangle here as a positive area, a triangle here as a negative area, and a hole of a circle right here as a negative area. This would only be 3 parts instead of 4, and it'd just make the calculation go a little bit faster. Alright, first thing that I do in this problem, exactly like the last problem. I go through and for each of the parts, I want to specify 4 things. I want to specify the centroid location, the area, the moment of inertia about x hat, and moment of inertia about y hat. So I set this up for part number 1. I'll let you go back through and verify each of these numbers and see where I got each of these numbers. For part number 2, this is what I have, again defining these same 4 terms. And for part number 3, I have these same 4 terms. So that's kind of just setting it up, specifying centroid, area, and moment of inertia about x hat and y hat based on what we're given from reference figures. So notice like this, for instance, this equation, pi over 4 times r to the 4th, comes directly from the reference figure, pi over 4 r to the 4th. So as I said, what I'm focusing on this question is really how do I calculate moment of inertia about the centroidal x and centroidal y axis. Well, before we get there, let's finish the other part of the question. What's I about x and I about y? Well, actually I can just use the same type of analysis that I did on the previous example. I have my composite area equation where I sum up the moments for each of the parts. In this case, notice that part 2 and part 3 are holes, so they have minus the moment of inertia. But this part looks exactly the same as last question. except for this is a minus because we have holes now instead of positive areas. Just like last time, when I'm moving, for instance, from the x1 hat axis to the x-axis, my perpendicular distance between those two is y tilde, just like in the last question, and then this is what I get for I about x. Now I want you to go back and verify each of these things, and you need to understand where this is coming from, but in essence it's the same as we did in the last example. So I'm just going to skim through it. For I about y, I have my composite area equation, again with the two negatives for the holes, and I have my parallel axis theorem for each of the moments of inertia. Also, just like last problem, the perpendicular distance between y hat and the y-axis is what we call x tilde. So really here, I now want to focus on how do I find moment of inertia about the x hat axis and the y hat axis. So remember, this is wanting moment of inertia about the body's centroidal axis. And it doesn't even really show it on this figure. So first of all, I would have to kind of estimate where is the centroid for this body. So I might estimate that the centroid for the body is somewhere in here. And then if I pass an x and y axis through the body's centroid, which notice I'll label as C, here are the two axes that it's actually talking about. I have the x hat axis and the y hat axis. So I'm trying to find moment of inertia about this axis and moment of inertia about this axis. So let's look at what that might be for the x hat axis first. So I want to write it out. If I want I about x hat, what I'll need to do from composite area method, add up I about x hat for part 1 plus I about x hat for part 2 plus I about x hat for part 3. But in this case, I'm not actually adding these others. I have holes for part 2 and part 3, so this should be minus. So then, moment of inertia about the x hat axis for part 1, I'm going to have to use parallel axis theorem. I'm going to take it from the part's centroidal axis and then move it with the parallel axis theorem to the body's centroidal axis. So I do that by adding some area times a distance squared. So this would be moment of inertia about x hat for part 1. Then for part 2, it's going to look very similar. And for part 3, also very similar. So what I need to specify here, I've already got these terms just like I had in the previous example, I about the local body centroidal axis. That's what's given to me from the reference figures. And then I already know the areas as well. So the only thing that's unknown in this equation right now is this dx hat. So I need to specify what are the dx hat for each of the parts. In general, it should be the perpendicular distance between the old axis and the new axis. So for instance, part 1 would be distance between x1 hat and x hat. So in order to help us find this, I'm going to go back and sketch out the part and the body. So I'm going to go and grab kind of this original figure here. And copy this down, paste it onto a new slide. I have the centroid location already plotted for the body. So remember, for the body, the centroid location is at some location coordinates of x and y bar. So these distances are labeled as x and y bar. Then, for instance, let's look at part number 2. Part number 2, its centroid is somewhere up here, C2, and it has centroidal x and y axes like this. Here would be x2 hat, and here would be y2 hat. Notice that part number 2, its centroid is located at some value which we call y tilde and x tilde. So for our moment of inertia calculation, what we need to get is we need to get the distance between the x-hat axis and for the part and the x-hat axis for the body. So here, what's the distance between x2 hat and x hat? It's just going to be the difference of y2 tilde minus y bar. So if I sketch it out, this, in other words, is my d x hat for part 2. So if I did it for the other parts, it's going to be very similar. I'll have y tilde minus y bar. And it doesn't really matter if y tilde is bigger than y bar or if y tilde is smaller than y bar, because I'm putting this into the parallel axis theorem. I'm going to square it, so whether the number is positive or negative won't matter. So I can generalize this and just say that, for instance, dx hat I, I'll put it down here, is equal to y tilde for the part minus y bar of the body. Now obviously here I'm going to have to actually find y bar. I don't know that, it's not given to me, so I'll have to find it. So I'll do the calculation for y bar here in a second. Before I get there, I also want to look at what would be I about y hat. For I about y hat, it's going to look very similar to this expression above, except everything's going to become y instead of x. So it may just be easiest if I copy this, and then I'll just replace everything where it says x with y. Couple more. Alright. So for dy hat I, that's the missing term in this equation. because we've already specified these for each of the parts and the areas for each of the parts as well. So now we're looking between, or actually for the perpendicular distance between the y hat for the part and y hat for the body. Using the same figure, we can calculate it exactly. What's the difference between y2 hat and y hat? Well, it's just going to be x2 tilde minus x bar. In other words, this is our dy hat here for part number 2. And if we generalize it for each of the parts, we can say dy hat for the part is x tilde minus x bar. So I'll have to go in and actually calculate x bar for the body and y bar for the body, but I know how to do that from the centroid chapter. I just use these things, or these equations that we've developed previously. And actually note, I've already calculated all the terms that are necessary in this equation. I have x1 tilde, I have a1. I have x2 tilde, I have a2. I have x3 tilde, and I have a3. Notice I have negative here for the holes. Remember, the holes have negative areas and negative moments of inertia. So for x bar, I want you to check this and calculate it on your own. 2.53 inches. For y bar, 4.62 inches. Now, everything is pretty much known. I can just go back into these equations for I x hat, I y hat, and calculate the number. So I want you to check this and see if we get I about x hat should turn out to be 370.4. I about y hat should turn out to be 119 inches to the fourth. So, next time it asks if I want to find the moment of inertia about the body's centroidal axis, whether it's x or y, this is then the process that you would have to go through. And the equation that we had right here, you could generalize to any other type of body, right? You would find I about x hat for the part, and then use the parallel axis theorem to move that moment of inertia to the new axis. And it's always going to turn out to be that this dx hat is y tilde minus y bar, and dy hat is always going to turn out to be x tilde minus x bar. So you don't need to derive this again. You can just kind of use the results that we learned from this problem in any future problems that are similar. Alright, that pretty much wraps up everything that we need to know about moments of inertia. We can now calculate moments of inertia about the x-axis and the y-axis for an area that's bounded by 3 or 4 curves. Also for some composite area that's made up of simple shapes. We can also find moment of inertia about a body's centroidal x and centroidal y axis. But I do want to go through one more question. I'm not going to go through this one in very much detail. I just want to point out something interesting whenever we have certain types of shapes. So here, for example, notice if I'm calculating moments of inertia, this time it's about centroidal x and y axes. I have, in essence, 3 parts here. I separated it into part 1, which is this rectangle, part 2, which is a semicircle, and part 3, which is a rectangular hole. So my calculation about my calculation for x bar would be equal to 0 because of the symmetry. I would have to calculate y bar in order to determine moment of inertia about x prime. Right? They use the symbol x prime for the centroidal axis. I usually use symbol of x hat. Notice here that y, the given y-axis, it shows us this is the centroid. Notice that the y-axis and the y-hat axis are actually the same in this case. Alright, let's go through a little bit of details. For part number 1, I can just define each of these terms. C, A1, I about x hat, and I about y hat, like I've been doing previously. For part number 2, I notice that this is a semicircle, so I go to my reference and find moment of inertia for a semicircle. So a semicircle has a centroid location that's given. It's 0 in the x and 4r over 3 pi in the y. But unfortunately, in this, we're not given I about x hat. We're given I about this x and I about this y. Right? In order to use parallel axis theorem, I can't use I about x. I need to be able to calculate I about x hat. So, for part number 2, when I set it up, I, as before, define the centroid location. Here, notice I'll have, for the y term, a 4r over 3 pi. That's from this location of the centroid. The area is just the area of a circle divided by 2. I about x hat, my reference figure gives me I about x is pi r to the 4th over 8. But I actually need to then calculate I about x hat. So how do I do that? Well, I know I about x from the parallel axis theorem should be I about x hat plus area times a distance squared. In this case, the distance here is going to be labeled this d, the distance in between the x hat and the x-axis. So although I'm not given directly I about x hat, I can calculate it as, from the parallel axis theorem, I about x, the given I about x, and then minus an a d squared. So that's where I get this term here. I have I about x, and then minus area times that distance 4r over 3 pi squared. So for semicircle, and there may be a couple other shapes like a quarter circle, if we're not given I about the x-hat axis, we may need to calculate it. And that's kind of the main thing that I wanted to show with this problem. It's a little bit unique for an area like a semicircle. Notice though that for I about y hat, it's the same as I about y, because for the semicircle, since the centroid x location is 0, y and y hat are the same. So I don't have to use any parallel axis theorem here. I just use pi r to the 4th over 8 like it gives me. The rest of the problem, I'll go ahead and put in this information for part number 3. I'll put in the information for the calculation of y bar, calculation about I x hat, and I y hat. So I want you to go through this problem and understand where each of these terms is coming from, and relating to what we've done in previous problems, we can see where I get this stuff right here, and check and make sure that you can get the same answer. Alright, as I mentioned, the main thing that I was looking at in this particular problem was I wanted to show that something interesting happens whenever we have a body such as a semicircle and we're not given I about x hat. Also note that for parallel axis theorem to work correctly, we have to use I about x hat right here, or we'll get the wrong answer. So that wraps up our study on moments of inertia. You can use the 2 moments of inertia homework to practice. The first homework, number 23, is over moments of inertia for an area that needs integration. And then homework number 24 is moments of inertia for composite areas. So you definitely want to practice those before you get to the final exam, at least a little bit. Otherwise, if there's a moment of inertia question on the final exam, which there's more than likely going to be one, you are going to struggle with that particular problem because you will have never tried to calculate it, and you won't know all of the details of the calculation. So, anyways, that wraps up moments of inertia. If you have any questions, let me know in the office hours or during the review session on Thursday.